Hello class, this is a video tutorial on radial surveys and trigonometry. So a radial survey is a diagram of a landscape observed from a fixed position, usually given as point O. Positions of landscape features, marked as vertices or just points with letters, are measured distances from point O and either a bearing from O or angles between each feature. So I've drawn an example of what this means. So here's a radial survey, actually two radial surveys, each showing the same piece of information. So here's that fixed point that we talked about in the center, and point A, B, C, and D might be, I don't know, this might be a waterfall, might be a tree, big rock, I don't know, a house or something, all measured from the point O. The distance to each point is measured from O. So this 4.7 kilometer is almost always referring to that distance from O to B. Likewise with O to A, that's 3.5 kilometers. And the bearing next to the point or the vertex is the bearing from point O. So this bearing here, O 22 degrees, is the bearing from O going clockwise to this point. So in reality, that angle here in black is 22 degrees. But we'll look at that later. Or the angle between each feature is already given. So take a look here. So the angle here can be found as 143. All right, and I'll go into a few examples how we can find that angle. Okay, so I hope that gives you an understanding of what a radial survey might look like. Okay. Oh, and also there might be more than 4 points. You might have 5, 6, 7, or 8. But I hope you can already see the triangles that are being formed. Alright, so let's do a few examples. So let's calculate the area of quadrilateral ABCD. Okay, so we want to find all this entire area here that I'm highlighting. How we're going to do that is actually by breaking this down into 4 different triangles. Okay, so we have triangle OAB, this triangle here. That's one triangle. We have another triangle plus the triangle OBC. So this triangle OBC. So this triangle here, that area, and it's going to go on like this. So the next triangle is going to be triangle OCD plus triangle ODA. Okay, so I'm actually going to do little mini diagrams like this to really help me visualize what I'm trying to draw. So we have triangle OAB first, so this is the first one I'm going to calculate. I know that that's 3.5 and this is 4.7. And now to calculate this area, I'm going to be using the sine rule for area. So area equals half AB sine C. So we have A and B, but the angle I need is this one here, which is this one here. How we're going to calculate that is by thinking the following. Consider that the bearing from north to this point here is 22 degrees. Okay, and now the bearing from north, actually use different color, from north all the way around to here is 306 degrees. But if we were to do a full 360, that's 360. That means the remaining amount here is 360 take away 306. Let me demonstrate that here. That is 360 take away 306, 54 degrees. So this little angle here is 54 degrees. And now that translates to this angle here being 54 plus 22, giving us 76 degrees. And that's going to be the area of triangle AOB. So let's plug this in. Half 3.5, 4.7 sine 76. I need half 3.5 times 4.7 sine 76. That gives me 7.98. Now the unit of measurement is in kilometers, so this is going to be in kilometer squared. So that is the result of one triangle. We're done with this one, and we're going to move on like this to find the rest, the remaining three. So if it helps, I'm going to draw again triangle OBC, like so, OBC, and that gives me a side 4.7, that is 4.4. Now the angle in between here, and we can calculate that by thinking of the following. Let's go back to our original drawing. The angle from north to here is 165, but the angle from there to there is 22. So if we do 165 take away 22, it'll give us this angle in between here, which is what we want here. So really, to find any angle between here, we just take its end point, 165, subtracted by the previous point there. So 165 take away 22, that will be 143. And let's now calculate the area of that one. Area equals half 4.7, 4.4 sine 143. Half 4.7, 4.4 sine 43. That gives me 7.05 kilometers squared. Rounding it again to 2 decimal places, and this will continue, and I will just finalize the remaining 2 triangles. You can pause the video and fast forward at any point so you can check your solution. So triangle OCD, I'm going to draw it out to make it easy for myself. There it is. OCD, that's 4.4 here, that's 3 kilometers. And we can find this angle very quickly by taking the end point, 250 degrees, take away the previous angle of this where we want to start, take away 165. That's giving me 85 degrees. Okay, focusing just on this triangle, area equals half 4.4 sine 85. Writing it in, half 4.4 sine 85. Whoops. There we go. 6.57 kilometers squared. one last triangle, triangle ODA. I'm going to draw this out as well. ODA, like so. Fortunately for me, I can use my iPad. 3.5, 3 kilometers. Once again, we can find this angle by taking the endpoint 306, subtracting by 250. 306 minus 250, 306, 56 degrees. Calculating this, area equals half 3.5 times 3 times sine 56. Writing this all in. Half 3.5 3 sine 56. Whoops, that's incorrect. Half 4.35 kilometers squared. And those are the 4 individual triangles. We can just add them all up together now. So highlighting the bits that we need this one, this one, this one, and this one. Adding them all together. So the total is 7.98 plus 7.05, 4.35 plus 6.57. Just using my calculator, make it easy for myself. 7.98, 7.05 plus 4.35 plus 6.57. This gives me a total of 25.95 kilometer squared. Alright, so I hope that gave you an insight into radial surveys and applying some trigonometry to some questions we might experience. I'll see you in the next example video where I apply the cosine rule. Best of luck. See you in the next video.